Okay, so our third type of chemical reaction, we had precipitation, we had acid-base, and now we're going to talk about oxidation-reduction reactions, or sometimes shortened to redox. Um, Oxidation reduction reactions involve the transfer of electrons from one species to another. So it's similar in a way to acid-base. It's just that instead of a transfer of a H plus, this time a proton, this time we're transferring an electron. Oxidation is defined as the loss of electrons, and reduction is defined as the gain of electrons. You can see a little mnemonic down at the bottom. Oxidation is loss, reduction is gain, oil rig, if you want to remember which one's which. You can't have oxidation without reduction or vice versa. They always occur simultaneously. So some examples of oxidation. If you take sodium metal and oxidize it, it loses 1 electron to become sodium ion. Iron loses 3 electrons to become the Fe3 plus ion. Reduction examples, chlorine gas can be reduced. Each chlorine needs to gain 1 electron, so a total of 2 electrons give you 2 chloride ions. Oxygen can be reduced by adding 4 electrons. Each oxygen will get 2 electrons and become the oxide ion, O-2. So, of course, reduction and oxidation have to go together. So here's an example of the rusting of iron. Each iron loses 3 electrons to become Fe3 plus in the rust. Each oxygen is reduced. It gains 2 electrons to become O-2 in the compound. And the balanced equation, of course, you have to have 4 irons. Each iron loses 3 electrons, so that's 12. Each oxygen gains 2. So there's 6 oxygen, so that's 12. So you have to have the same number, which we'll see in just a minute. But each iron loses 3 electrons and each oxygen gains 2. So another example of an oxidation reduction reaction is an iron nail stuck inside a copper sulfate solution. Here's the molecular equation. Iron on the left, you can see, has no charge. On the right, it's in a compound, so it's a +2 charge because it's sulfate is a -2. So Fe is a 2 plus. So iron has lost 2 electrons to become Fe-2. Copper sulfate, copper on the left, is a +2 ion, and it has gained 2 electrons to become solid copper. Here's a picture of the of it. You can see here the copper ion in solution becomes copper metal. The iron metal becomes iron solution, and a couple of things happen. You start to see the copper plating the nail, and so the copper is depositing itself on the nail. And you also see that the copper is being used up in solution. Iron happens to be kind of a yellowish or very colorless solution, and so the blue fades. And you can see that on the far right. Okay, so the net ionic equation shows it even better if you break all those ions apart. So the FeSO4, I'm sorry, the Fe is on the left. The copper is with the sulfate, so Cu2 plus SO4 -2. And then on the right-hand side of the equation, the Fe2 plus SO4 -2. The SO4 cancels because those are spectator ions. And so now you can clearly see that the Fe has lost 2 electrons, so that it was oxidized. And then the copper has gained 2 electrons and it was reduced. And so these both happen at the same time. Interestingly, if you were able to do, which we're going to look at much more in the second semester, if you have copper and iron in separate containers and put a wire between them, you can get electricity to flow. Those electrons can flow outside of the container, and that's how batteries work, sort of on a very simple scale. Okay, so one thing we need to be able to do is to tell if something's been oxidized or reduced, and the way you do that is by looking at oxidation numbers. So the next few slides will be going over um, how to figure out oxidation numbers. Okay, it's a way of keeping track of electrons, and we can see if something has gained electrons or lost electrons. So the oxidation number, which is also considered the oxidation state, is the actual charge of the atom if it exists as a monoatomic ion, which it always doesn't. It doesn't always exist that way, but we're going to calculate it as if it did. So it could be the hypothetical charge of the atom inside a substance. And so we're going to go through the simple rules. Let me go through them first, and then I'll go through some examples. So these are the oxidation number rules, and by using all of these, we can figure out the oxidation numbers. Some of them are very specific, and then others we can figure out using the rules. So the first rule, which is the easiest, is that the oxidation number of any atom in an element is 0. So, like in the last example, zinc was a metal. It didn't have a charge, so its oxidation number is 0. So that includes elements like oxygen, nitrogen, hydrogen, even though they're like it's O2, N2, H2. Anything that's by itself and doesn't have a charge, the oxidation number is just 0. Okay, if you have an ion that's all by itself, so a monoatomic ion that's by itself and has a charge, then the oxidation number is just equal to that charge. Now, that means that group 1A and 2A metals, if they're in compounds, will also be positive 1 and positive 2 respectively, because they don't ever change their charge. And so if they're in a compound, they're an ionic compound. That means that they have a +1 if they're in group 1A or a +2 in group 2A. So even if they're in a compound and you don't see the charge, they are considered monoatomic ions. And then any other metal that shows its charge, that is its oxidation number. Oxygen, rule 3, says that the oxidation number of oxygen is almost always -2. So in most of its compounds, it's a -2. There is an exception. If you've got a peroxide like H2O2, the oxidation number is -1 for oxygen. Usually what I do is I go along assuming it's a -2, and then if some other rule contradicts it and it won't work out, then generally it's the oxygen that needs to be changed to a -1. But for the most part, you can assume it's a -2. All right, rule 4, hydrogen. If hydrogen is in a compound, it is almost always a +1 oxidation number, unless it is paired with a metal. So if it's written second and it's paired with a metal, usually the metal is written first. And hydrogen, if it's written second, then hydrogen will be a -1. But most of the time it's a +1. Okay, halogens. Halogens we know are those elements in group 7A. Fluorine will always be a -1. And if the other halogens are in a compound with anything except another halogen or oxygen, they'll be a -1 as well. However, they can have different oxidation numbers if oxygen is involved in the compound or if other halogens are involved, and we'll have to look at that in just a minute, what you would do in that case. And then this is the probably one of the most important rules, is that in a compound or an ion, the sum of the oxidation numbers for each individual atom, if it's a neutral compound, the sum will always equal 0, and if it's some kind of polyatomic ion, the charge of the oxidation number of each individual atom will have to equal the charge of the ion. So I think the best way to go through these rules is to just show examples. Okay, let's do a few examples. H2S. What is the oxidation for S in this compound? Well, if we use rule 4, H is a +1. Since there's 2 H's overall, The oxidation is a +2, so sulfur has to be a -2 to balance this out. Okay, for S8, since sulfur is in its elemental state, it will be a 0. Even if you didn't remember that, you'd say, well, what does sulfur have to be to equal the total charge of 0? Well, it can only be 0. For SCl2, we can use the halogen rule. Since halogen is not with oxygen, each chlorine is a -1. So that means to balance this out, sulfur has to be a +2. Okay, for Na2SO3, we can use first the second rule that says that Na in any compound is going to be a +1. There's 2 of those. Oxygen, there's 3 of those and they're each -2, so that's a -6 and a +2, so sulfur has to be a +4 to balance that out. Sometimes you can use a little bit of an algebraic equation here that the total charge is 0, or the total charge is 0, so there's 2 +1s, whatever sulfur is, 3 -2s, that'll balance out. You can solve for sulfur and you get +4. In the same way, SO4 -2, since we have 4 oxygens and each of them are -2, but now the total overall oxidation state is -2, so the total has to equal -2. So what will sulfur be to add to -8 to give us -2, and that's 6. Okay, so you can see the little algebraic equation there. All right, a few other examples. P2O5. Well, with nothing else to go on, we'd start with the oxygen rule that says that oxygen is a -2, so overall that's a -10. So in order for phosphorus to balance that, you have to have a +10, so each one has to be a +5. NaH, Na in any compound is a +1, and H's rule says that if it's with a metal, it's a -1. So H is a -1 and Na is a +1. Okay, this next one will show the kind of exception rule to oxygen. So your initial thought might be oxygen is a -2, and so that would be a -4 overall, and so barium is a +4. But then you get caught up because barium is in the second row, so barium is always only a +2. So in that case, you have this kind of problem, and so that is generally a case when oxygen will not be -2, and so in fact, barium is a +2 and each oxygen is a -1. Okay, and then finally Cr2O7, since the complete charge has to equal -2 and there's 7 oxygen, so -14, then the total chromium has to be +12, and so each one has to be a +6. And if you want to set up the equation, -2 equals 2 times whatever chromium is, plus 7 times -2, and then you can solve for chromium. All right, so let's look again at the reaction of iron with copper sulfate. What I want you to notice, again, iron has been oxidized, it lost 2 electrons, and copper has been reduced, it gained 2 electrons. This one is actually balanced, although you might not know it. We can pull this apart into what we call half reactions. Okay, so half reaction is just the part of the oxidation, just one half of it. So either you're writing the oxidation or you're writing the reduction. So in this equation, the iron going to iron 2+, giving off 2 electrons is the oxidation half reaction, and then the copper being reduced, copper adding 2 electrons to become copper, is the reduction half reaction. If you notice, if you add those back together, these have the electrons, and then the 2 electrons can cancel, and so we get back to our original equation. Okay, so sometimes we also use the term oxidizing agent. So an oxidizing agent is something that oxidizes something else, and it itself is reduced. And then the opposite, a reducing agent, is something that reduces something else, and it is itself oxidized. So in this equation, the iron, which is oxidized, is actually the reducing agent, and the copper, which is reduced, is actually the oxidizing agent. So just flip that around. All right, so let's look at one other example. At first glance, this equation looks to be balanced. Okay, zinc plus silver gives me zinc ion, or zinc plus silver ion gives me zinc ion plus silver. But remember what I've said before, you want to make sure in an equation that the charges are balanced as well. And so this is not true. Notice on the left we have a positive 1 charge overall, and on the right is a positive 2. So if we split these up into our half reactions, we can actually balance it correctly and see what's happening. So again, the number of electrons lost have to equal the number of electrons gained in the reduction half reaction. So again, if we split it up, zinc becomes zinc 2 plus and loses 2 electrons, and that's how we can write it. Silver, that's the oxidation half reaction. Silver, on the other hand, Ag plus, will gain 1 electron to be reduced to silver metal. Okay, so they don't have the same number of electrons. So what do we need to do? Well, we're going to have to double the reaction involving the reduction so that we can have 2 electrons. So if we double everything, we have to double them all to keep it balanced. Now we have 2 electrons on the left, 2 electrons for being reduced, and 2 electrons on the right for being oxidized. So now if we add these reactions back together, the electrons will cancel. So you can see there's 2 electrons on the right hand side, 2 electrons on the left hand side. They cancel out. We can rewrite the equation, and it is balanced both in number of each individual atoms, and also it's balanced in charges. We have a total positive 2 charge on the left and a positive 2 charge on the right. There are some negative ions, they're just not showing up here. All right, so we've talked about 3 types of reactions. We've talked about precipitation, acid-base, and oxidation reduction. Now we're going to talk about just a different way to categorize chemical reactions. These are more by mechanism, like how they're actually, what the products are, and you'll see in just a second. So there's generally 4 types of reactions: combination, decomposition, displacement, either single displacement or double displacement, or combination. Those are my 4 types of reactions. Okay, so we're going to look at each separately, and we'll also talk about it in terms of redox or non-redox. And actually, acid-base reactions, even though they're not precipitate reactions, they act in a similar way. So they're non-redox. So we can categorize acid and base or precipitation reactions as non-redox reactions, and then of course, redox reactions are redox reactions. Okay, so a combination reaction, what you want to remember about combination is that, just like the name implies, 2 things will combine to form 1 product. So if you see something that only has 1 product, that would be considered a combination reaction. So here's an example of that. 2 sodium plus chlorine gas will give us 2 sodium chlorides. There's only 1 product. NaCl. Combination reactions can be redox reactions, which this one is. How can you tell if it's redox or not? You're going to have to look at the oxidation numbers. So here, if the oxidation number changes, it's a redox reaction. Here, sodium on the left is a 0 oxidation number, but on the right, since it's in a compound, it's a positive 1 oxidation number. So it's changed. It's gone from 0 to positive 1. So it has increased its oxidation number, which means it's been oxidized. Chlorine has gone from 0 on the left because it's a neutral compound. Cl2 is neutral. So it goes from a 0 oxidation number to a negative 1. So it's been reduced. And that's how you can tell if it's a oxidation reduction, which this one is. So this is just showing the reaction of sodium, which is that sort of shiny metal on the glass plate there, and then chlorine is inside that bottle. It's that greenish gas, and then they just put a little piece of the sodium inside the gas, add a drop of water, and you get this explosive reaction. And then the result is that you'll have salt, sodium chloride, at the end. There's some YouTube videos out there. If you just Google reaction of sodium and chloride, you'll see this in action. Some combination reactions are non-redox reaction, and those will be things like precipitate reactions, or here calcium oxide reacts with sulfur dioxide to give us calcium sulfite. And this is also combination because there's only one product. But if you go through and calculate the oxidation numbers, they don't change at all. So this is a non-redox reaction. The second kind of reaction, a decomposition reaction, is one, just like the name implies, something, a single compound reacts to give two or more substance. So in other words, one thing is breaking down into two or more things. So an example is mercury oxide. As a solid, can break down into mercury metal and oxygen gas. This is considered a redox reaction. And we can also have decomposition that is non-redox. An example is calcium carbonate breaking down to give us calcium oxide and CO2. As you can see, calcium carbonate is limestone, and if it's under and it can sit around or under enough pressure, it can decompose into the quicklime and CO2. Here's a picture of the mercury oxide breaking apart into mercury liquid. Up here, the silver, you can see the mercury liquid, and then the oxygen is the bubbles kind of forming. And the orange stuff is the mercury oxide. Okay, there are two types of displacement reactions. A single displacement or a single replacement reaction is a reaction where one element reacts with a compound displacing an element from the compound. If you look at this one, zinc is all by itself, and hydrogen is with chlorine, and then on the right hand side, zinc is with chlorine and hydrogen's by itself. So zinc has displaced hydrogen with chlorine, so only one thing has been displaced as a single displacement reaction. All single replacement reactions or single displacement reactions are redox reactions. They always are. If you look at this one, zinc goes from an oxidation number of 0 on the left to +2 on the right. Chlorine actually stays the same. It's -1 on the left and -1 on the right, but the hydrogen goes from +1 on the left to 0 on the right. So hydrogen is reduced and zinc is oxidized. So this just shows a picture of this single displacement reaction. You start out with zinc metal, and then you've got hydrochloric acid dissolved. So the hydrogen is the little blue dot that's dissolved hydrogen ion. And then after the reaction, the zinc has gone into solution and formed an ion, and the hydrogen has become hydrogen gas and escaped from the bowl. A double replacement reaction is a reaction where two elements or ions are replaced. They replace each other. So there's two compounds, and two of them is like a swap, where one replaces one with one compound, and the other replaces the first one in the other compound. Precipitation and acid-base reactions are all examples of double replacement reactions. Double replacement reactions are never redox reactions. So here's an example: calcium hydroxide and sodium carbonate, and then notice that the calcium replaces the sodium to form calcium carbonate, and then sodium replaces the calcium to form sodium hydroxide. This happens to be an acid-base reaction, and if you were to go through, all the oxidation numbers would remain the same throughout. So again, if you do the double swap, like a precipitation or acid base, that is a double replacement. Finally, we have one other category called combustion, and it gets its own category. It's really when a substance reacts with oxygen, usually with the rapid release of heat to produce a flame, or just a lot of energy, release of a lot of energy. This is actually the rusting equation again, but if you took iron, like steel wool or iron wool, and react it with oxygen and lit it, it would burn brightly and give off a lot of energy. So this is a combustion reaction, iron. And all combustion reactions are this is iron wool. All combustion reactions are redox reactions. So iron is going from 0 to +3, so it's been oxidized. Oxygen is going from 0 to -2, so it's been reduced. Another combustion reaction that we are very familiar with is reaction of some kind of hydrocarbon with oxygen. This happens to be methane, natural gas. If your house is heated by natural gas, it's a combustion of methane with oxygen to form CO2 and H2O. Some other common combustion reactions, gasoline is a combustion reaction where you have a variety of hydrocarbons, carbon and hydrogen compounds. Butane, if you have a butane lighter, it's carbon hydrogen. It's C4H10 is the compound. But again, those are all combustion reactions. And this is just an example of iron wool or an iron wool pad being burned and becoming iron and oxygen, or becoming iron oxide. Iron reacting with oxygen to become iron oxide.